All right. So now we should be streaming. Oh my goodness. For just what? What is insane? The cost? Oh, well, I'm more like at the uh anyways. How are we doing? Week uh what is it? 8? Are we on 8? Oh my God. Oh, week 8. Oh my goodness. Well, week 8. How are we feeling? Yay? Nay? Nay? Indifferent? Whatever. Um, but today, I guess is like a bit of a slower news week, but there's still some interesting topics. Um, Good news. If you wanted VR to succeed, well, it is succeeding because the Quest 3S is now the top selling devices on Amazon's video games category. And this implies that it's not just like the best selling VR headset, because obviously, it will be the best selling VR headset because who else is really realistically challenging Meta right now besides themselves? But apparently, it's not only the best selling VR headset, just any sort of video game console. So even against things like PlayStation or Xbox or Switch or whatever, Quest 3S is doing pretty well. And that's pretty exciting because especially if any of you want to make, careers out of this, either in game development, application development, VR development, whatever, like I do, this is only good news. So hoorah, go Meta. Um uh yeah, it's awesome. But, for every good thing, there's a bad thing. So, Meta has canned the Quest Pro 2. Now, if do any of you know what the Quest Pro was, the original Quest Pro? Yeah. So, I mean, it's that in the pictures. It was Meta's first attempt at like a productivity VR headset. I actually remember when it was announced. I was in Math 240 in my discussion watching the Facebook live stream because they refuse to stream anything on like actual good platforms like YouTube, but that's besides the point. It came out, and then their initial push was like, uh, you could be, productivity in the metaverse. Like like that was their whole spiel. They were trying to emphasize all the cool use cases you had, where you could theoretically put this on, you could have a bunch of monitors, you can do all of your work, yada yada yada, and it made sense, at least in theory, having the perfect setup that's portable like this. They even got Microsoft on board. Like the CEO of Microsoft came on stage and was like, "We're going to make Word for this, Excel, all these different productivity apps. We're going to bring them over to this platform." But what ended up happening was that the device itself was more of a forced product that had to leave the lab rather than something that was truly ready for consumers. So, for example, the 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 displays in this thing were like good, but not quite good enough to do like write a Google Doc or work on an Excel spreadsheet. They were kind of lacking that like fine clarity that you need to actually get real work done. And on top of that, this was like on top of the metaverse boom, where like a lot of companies are coming out like you can buy virtual land in the metaverse and not being very descriptive beyond that. So that and combined with like the kind of lackluster displays, it didn't sell so well. It was also originally $1,500. That would also contribute to it. And the cameras on it were also garbage. In fact, it had color pass through, so you could actually see like real world colors compared to its predecessor, the Quest 2, which was just black and white. But the way it did colors is that it actually took a very low resolution color sensor almost, and it sort of overlaid that data on top of the black and white feed, and it kind of gave this weird blotchiness. And so, needless to say, that didn't sell well, and now the Quest Pro 2 has been, canned. But wouldn't look into this so harshly because they're probably trying to double down on the AR glasses that we saw a few weeks ago because, that makes more sense from a productivity device. Instead of wearing this big bulky thing. So we'll see what comes of that. But oh well. What else? Oh, this is good. So because they still are kind of interested in doing work in the metaverse, or not just the metaverse, but just in VR in general. And so did Apple with the Vision Pro, the idea that you can, do all of your productivity stuff. One feature is that when you're in an immersive environment, you want to be able to see your keyboard. Like you want to make sure that your fingers are where you think they are. If there's that like pesky key that you can never remember where it is, you want to be able to sort of cut through the virtual world to see your real keyboard. And both companies have had this feature, but sort of not perfectly, because in both cases, to the best of my knowledge, it only works with specific keyboard vendors. So you had to have a very fancy keyboard from either Apple, Microsoft, or Logitech that was recognized by the headset in order for it to cut through properly. Which means that if you're like me, let's see, and you have this snazzy portable keyboard that like folds up in your bag or whatnot, it's not going to get recognized by the headsets at all, because this is just some no-name company Proto Arc. I'm sorry if we have any Proto Arc fans here, but like no name company, and so it's not going to be. It's not their headsets are not trained to recognize this keyboard, and so it wouldn't cut through. But with this update, you can theoretically do any headset, which will be kind of cool. So that means that I would be able to use this keyboard or any keyboard that you have. You could just plug it into your headset or connect over Bluetooth, and you should be able to see it through the virtual world, which is pretty nice. What else? Vision Pro. Uh, Apple. Mark Gurman. Does anyone know who Mark Gurman is? No, nobody. Very reputable Apple leaker or source of Apple news about the company. And for many years, he's been reporting on like what they're going to launch, what they're going to do, what their plans is for the future, the roadmaps. And he's generally regarded as being very trustworthy or being accurate. And well, we he says that like they're working on a non-pro version of the Vision Pro headset that'll be around $2,000. Now, $2,000 is still a kidney, so but it is at least compared to the current price of starting at $3,500, it at least it's only one kidney, you know, a little bit better. And one of the things it's going to sacrifice is it's going to sacrifice, that like, oh yeah, it's called like I don't even remember what it's called. Eyesight, yeah. The display on the front that makes it so that you can see like the person behind it, like their eyes or whatnot. They're just going to ditch that, at least the room or two. And they're going to use, probably cheaper materials, not have it be the most metal and glass beauty thing ever. Like, it's not going to be the most beautiful thing, but it'll be more affordable. And realistically, Apple does have to do this over the next few years if they want to kind of be competitive, because obviously they can't keep selling at like these ridiculously high prices, because it's only going to attract, enthusiasts or developers, and it's not going to have a chance to be breaking into the consumer market. Hello, Jack. So that'll be exciting. Oh, and it was rumored next year, as early as next year, we could see that like lower cost device, and then like apparently 2026 they're going to make the Vision Pro 2. That would, you know, new sensors, maybe lighter, hopefully, but we'll see. Also the Vive Focus came out recently and it's been getting into the hands of reviewers, and so far, I think the reviews have been pretty okay. This company, HTC, they're the ones to make this headset. They also have made a bunch of phones in past. They have this tremendous curse of releasing headsets that are theoretically oh so great, but then they always fall on their face in one way or another. They always either lack some feature, it is too uncomfortable, it's always something that holds them back from actually making a good headset. And maybe that curse has been lifted with this headset, because this is a $1,000. It is $1,000. By no means is it cheap, but it has a bunch of technologies built in that no other headset really can offer all in one. It has face tracking, so for any games or applications that you want to be able to show facial expressions, they will. You can, it has all that features built in. You can work with it out of the box. It has eye tracking, so you get the benefits of what's called foveated rendering, as we talked about in weeks past, where you can just look at the thing you want to look at, and then um, you only render in high fidelity what you're looking at, so you get some performance savings. Also, can be applied to an avatar. And last but not least, this can directly connect into a PC. So if you don't care necessarily about on-the-go performance, and you just want to be able to wire into your big gaming PC that's going to, perform a lot better, you can do that. So not certainly not for everybody, but for the enthusiast category, instead of it is a pretty nice all-in-one bundle that we haven't seen in a while. Because the Quest Pro was our previous bundle, with like all the face and eye tracking, but it wasn't, you know, it was more productivity focused and not so much gaming. So this would probably kind of restore the balance. Somebody mentioned earlier. Oh no, it kind of came up earlier. That are the idea. So like, I don't know if you, how many of you get Macs, but a new feature that came out recently was that you can actually like open an app on your Mac and then actually control your phone straight from your desktop. Like you don't even have to like touch your phone. And they might be bringing that over to VR soon with Motorola phones. Now, I don't remember what phones Motorola makes. I don't think they've been a I mean, I haven't been so vested in the Android world, so I don't know how if I can point to a flagship Motorola model phone that exists right now. But for people who do have one, it's kind of exciting because um, theoretically, with the Smart Connect app or whatever, I don't know if there's like a I know you can barely hear that, but it's basically, I think Zuckerberg just kind of announcing that like, you know, their visions are aligned. But that would be really nice to be able to use your phone in VR because a lot of the times, you know, that's still an inevitability. You have to use your phone some way or another. And if you don't have to like look through the cameras, you can just like directly kind of feed it into your VR experience. That would be pretty nice. But I don't have a Motorola phone, so hopefully Apple can bring it equivalent soon. Or bring it to more headsets. Oh, and this is sort of like a little extra for me for those Unity developers. This is technically not very new news, but this is wild. So, as part of Unity 6, which is sort of Unity's newest version of, or major version of Unity that they're bringing soon, it's still in a preview stage right now. They have what's called this behavior graph feature, which um, this is a 20-minute video. It is kind of technical, but long story short, it basically will allow you to write kind of through this drag and drop interface, define a lot of the logic of your game without really having to write code. So for example, you can see here that like, you know, we have like an on start thing. So when your game starts, you randomly pick through either saying, here I go, and then moving through some predefined path that you define, or you can like have it, I don't know, navigate to somewhere else, but the gist of it is that you can do a lot of this sort of game, like high level game logic just by drag and drop and visual interfaces, which we've seen that a lot in the Unreal Engine with their blueprint system. Because oftentimes when you're doing that kind of high level design, you need not have code that like you don't have to really write code. In fact, writing code is often cumbersome. Oh, it's not. Wow. Well, wow. Okay. Well, here's a new news article. Uh, Well, Unity 6 is now out. So that feature that I just mentioned, well, guess what? It's here. It's no longer a preview, as Ian said. That's excellent. Uh, this comes with a whole bunch more that I'm not prepped on, and I haven't really tried too much yet. But long story short, it's going to be making, you know, the cliche. It's going to make making games a lot easier, and especially with like these visual interfaces, it'll be really nice because I was basically I had to do this in my own project yesterday, like this high level game logic, and you know, it I did it through code, and it was just kind of cumbersome because a lot of the time I just have these really simple actions that I don't want to write like the whole boilerplate of like copy and pasting all these classes everywhere, yada yada. Like stuff like this would be really cool. And I'm excited because it's going to make game development more accessible as well. But that's basically it, I think, for our big topics this week. I do want to remind you all that as part of going forward, we now have this sort of like form where you can, you know, if you ever want to talk about something or you ever want to showcase some of your own creation, you can do so here in this form. Like if you want to present and like individual showcase. I don't think we have anybody for today yet, but the option is there. You know, you don't have to, but if you ever have something cool, you can show it off. And I know that you know I'll go quickly because you know we want to get to the fun shader workshop. But I have something pretty cool that I wanted to show off. Uh, let me show it off here. As a side project of mine, and I actually open into kind of making it, maybe if anybody does want to help me on it, I wouldn't mind. But I kind of want to make this app that I call Desk Traffic Control. It is based upon the flight control game that my siblings and I used to play like a decade ago. It's kind of old. Basically, the goal of the game is really simple. You just land planes at like airports and you make sure they don't crash into each other. And what I'm trying to do is kind of take this, but bring it into a mixed reality format and add like the third dimension to it. And in doing so, I want it like kind of like this kind of vintage format, like kind of theme or vibe or aesthetic to it. So I could just add a score counter, right? Like just have like a piece of text floating somewhere that just says you have landed zero planes or one plane or however many. But I thought, you know what, that's boring. Can we do better? And so what I made is what's called a split flap display. So I'll get this running. Uh, which is not count. Oh, I know why. Okay. But basically, this is a fully configurable split flap display that you can kind of show whatever you want on it. So, oh, okay. So let's see. Uh, right now, it's just displaying numbers. So I can, up here, there's like a really tiny text box. So if I put 1, 2, 3, 4, it flips through like that. And I plan to use this for like the plane counter, right? So if you land like one plane, it's going to go one, and I can use this to display high scores and whatnot. I think it's pretty cool because it's like it even does, I don't know if you can hear, it does like a little like tick, 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 tick as it's going through. But how it works behind the scenes is, for those interested, is that it uses, so each kind of black square here is what I call a flap. And has anybody ever worked with Unity's UI system? Have you ever made a UI in Unity or anything like that? No? A little bit? Well, basically, what it's doing is that each of these squares has what's called a canvas. So that's basically a place where you can add UI elements. And the trick is you add like a text label, but what I do is I'm offsetting it a little bit so that it looks like it's sort of this one continuous thing. So there's a label here at the top half and at the bottom half, and they're both set to display 0. And through this offsetting, it makes it look kind of continuous when it's not, and that's what allows me to flip through it. And the other cool thing is that because these are labels, I can put whatever like alphabet per se I want on there. Right now, it's just displaying numbers, but with a very simple fix, I can come down here. Uh, there's like this alphabet parameter. I can set it to A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now, when I have that defined, I can now display words. So I can say Ian. Well, and oh, I have to clear it out though first. And then I'll changing it midway through its running is a little bit iffy, but when you do have it right, you can flip through anything. So if you ever want to learn more about how that works, if you want to talk to me afterwards, I'll be happy to explain to you how like even more about how it's efficient and whatnot. It's really cool in my opinion, but I'm not biased. Uh, but yeah. So once again, that's kind of like my showcase. But if anybody else, if you ever want to show something off, just let us know. And in terms of project updates, Ian's not here. Ian W. He's the one leading the VR horror thing. He's in DC this week. Uh, Jack, I know you've kind of been ill for the past few weeks, but and we'll order parts for the glove stuff. Yeah, so that'll be fun. Uh, but any questions, anything before you get started with the shader workshop? Any comments, any insights? No? All right. Well, without further ado, we can begin everybody's favorite shader workshop when I make sure that I have the right projects open so I'm not caught that off guard. Okay, cool. Go here. All right. Welcome to Shaders and Shader Graph. So This is a very cool workshop, one of my favorites to do because it's just really awesome. Normally, as we'll see, to do live visual effects in video games or in 3D applications in past, it requires you to code up what's called a shader, as we'll see. And that the way it was done before was all through this text thing. It was all kind of cumbersome, but through this thing called shader graph, as we'll see, it gets a lot more fun and a lot more visual. So to begin, uh, I I like to have this challenge where I kind of demonstrate a point, but I don't have a lot of markers, and I don't know if those markers on the board work. Maybe, maybe not. Some of them do. We could. I mean, we could give it a shot. Let's see. Maybe we can have some fun. If a lot of these are dead, I won't try this, but it is kind of fun. Let's see. That one works. That one, okay. I guess it works. All right, we'll try it. It's gonna be like a half effort work. It won't be as great with all these colors, but we can kind of still achieve the point. So I'm gonna need one person, just one. Okay, you're gonna take that. I'm gonna need three other people. You want one? Well, I volunteer you. All right, I need two more people. All right. I don't know how this is gonna work, but we'll see it. So, Jack, my one person, I want you on the left side. My group of three, I want you over there, but on the right side of the whiteboard. All right. Your goal when I flip the slide is to draw what's coming next as fast as possible. Don't worry about colors. Just try to like draw. It'll be in like a grid. It'll be pixel art. This will be a bunch of squares. So try to draw that. Ready, set, go. Draw this as fast as possible. The boxes. Oh yeah, no, I used to do a grid based on this. Oops. Actually, no, this will work in my favor. You don't have to draw the grid. Why? No, uh, because when I made this originally, it was around the Among Us height. Sorry, not sorry. And I'll give you like a minute or two left. You don't have to finish, but I'm just also, you've already proven my point that I'm gonna make. All right. Well, wow. Well done. 'll give you 30 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, and pencils, well, markers down. Okay. So if you back up for a second, what we'll notice, hi, Arig, is so we had Jack. He's one person, and he drew pretty well. And we have three people here who drew on this side. He didn't finish, and they're of, let's say, varying quality. But that still fits my analogy. What you'll notice is that the Chiba 3 drew 3 in the time that it took Jack to drew 1. And even though Jack, I mean, yours is pretty clean, in terms of throughput, you got more out of this side. This is an analogy that I'm trying to make between two pieces of computer hardware. Can anybody guess what they are? Huh? The GPU and the CPU? Yep. There you go. CPU. So Jack is a CPU. Very apt at drawing clean stuff. Great. Well done. Applause. But Jack is only one person like your CPU. So you can only do one thing at a time versus the TGPU, you know, I'm not going to discredit your artistic abilities, but for the sake of a metaphor, you're not quite as good as Jack is doing as doing any particular task really quickly, but there's more of you. So you can do more work in less time. And most crucially, you can do that work in parallel, or you can work together to draw all at the same time. And that is extremely important, as we'll see. So, why the heck do we need a graphics card in the first place, right? So there is some code here, but you don't have to be a coder necessarily to understand it. Let's just take the example. You have a monitor and you're trying to fill it up with the color red. That's it. Just the color red. Now, for you people maybe who are in your intro to Java classes or have only done CPU programming, your first intuition is you're going to you're going to set up two for loops. You're basically going to go through every single Y coordinate, every single X coordinate, and set that pixel to red. But let's say that to set a pixel to red, it takes 0.00001 seconds, a very small amount of time. But the problem is that, you know, you have 2 million pixels to go through on a monitor. And so what ends up happening is that even though that's like the CPU is theoretically very fast, that 0.00001 second adds up. And you end up spending 20 seconds filling up that monitor slowly, which I don't know about you, but I like to measure my games in frames per second, not seconds per frame. So, uh, and clearly, you're only getting 100,000 pixels a second at this rate. And if you want to have anything be decent, maybe target at least 60 frames per second, you're going to need to be pumping out 124 million pixels per second. So clearly, this is going to cut it. But can anybody kind of tell me the intuition of why is this so slow? Correct. And doesn't need to do one pixel at a time. No. So as you pointed out, crucially, like the understanding is that to set any of these pixels to red, you're all setting them to red. You don't need to actually wait for any of your like predecessors to be set before you can set the pixels. So if there was a way to magically kind of set them all at once, we'd be much faster. And hint it, nudge, nudge, there is a way. Yeah. So this is where the GPU comes into play. It's called the graphics processing unit GPU. And its specialty is that it can take all these computations and it does them in parallel, often with thousands or maybe even tens of thousands of like little tiny CPUs, if you will, all doing the work. The trade-off is that any of these individual CPUs is less capable than your full-on CPU. And it's also less efficient, it's less quick or has a slower speed or whatever. So like the analogy is like you might have like a really good artist that is your CPU can draw very good, and your GPU might be a 10,000 student classroom of kindergartners who aren't going to draw as well, but they're going to draw more stuff in the time that it takes you to draw one thing. And oh, I mean, okay, we'll say that like maybe high school is because the GPU is still it is still kind of each core is still powerful, but the way that we program a GPU to draw anything onto the screen is through what's known as shaders. And shaders, due to this sort of parallel nature, you kind of have to develop a different mindset for them, as we'll explore. It's different from what traditional programs that you might run on your computer. It requires a different mindset of thinking, but it's actually not too bad. Um, so what is a shader? So to achieve that parallelism, to like divide work amongst the army of kindergartners, you have to be able to break apart one problem into many smaller problems in order to solve them in parallel, right? Because it's not enough to just take one bigger problem and like try to give everybody to divide, on it. You need to have some way to meaningfully make it work so that it can be completed without having to wait on something or like get locked. Like I have to wait for this guy to finish before I can do my thing. No, it has to be a completely separate problem so that you can work without any bottlenecks. And they're kind of function like, and by that I mean that you cannot really have any global variables in shaders, asterisk, in the sense that if I'm drawing something on this corner of the screen, I can't set a variable or add like a coordinate to a list and then have some other pixel on the screen be like, oh, okay, well, this pixel set that, and now I'm going to read it. There's no communication between uh, your um, your shaders per se. They all have to basically be laser focused. They take in all the input they need, and then they provide an output. They can't communicate with each other. So those kindergartners, you can imagine, they're those like plastic folder dividers that they try to use in like elementary school to divide you in your tests. That's basically what's going on. They can't talk to each other. And to emphasize that, like data is going to flow one way. So when your shader starts, it's given the input of what to draw, and there's no going kind of around in cycles, contact. Like it's going to be a straight through process of you take the input and you eventually provide the color at the end. I know that's kind of all abstract right now, but we'll kind of delve into what this means in detail later. So how does it actually manifest in Unity? Well, in Unity, there's an important distinction to make. There are shaders and then there's materials. Have any of you worked with the materials in Unity? So, it, yeah, similar. So, an important distinction to make is that a material by itself does not render anything directly. What a material does is that it picks the shader program to run, and then it provides some input to it. So, when you want to make a wood material in Unity, what you're really doing behind the scenes is you're saying, hey, I pick this shader to ultimately render to the screen, and I'm going to provide it like the input of the wood texture, the like amount of shininess, some parameters about like brightness or whatnot. That's what the material is. It is just specifying the input to some shader program that you're defining. So when you're doing this programming, you're not necessarily coding up a custom material. You're coding up the custom shader that the material is going to feed data into, as we'll see later. But that is an important distinction to make. And if you ever get trivia in Unity for like what's the difference, oh well, now you'll know. And we'll also go over some more basic terminology. When we represent anything in computer graphics, we usually do so through one of like a framework or a combination of these three things. So you have what's called a mesh, and this is basically the geometric structure that composes whatever kind of 3D object you want to make. And crucially, this is just the geometry. There's no notion of color. There's no notion of shininess or anything like that. It is just uh, a set of like points in space that are connected to represent a 3D object. Then, when you want to start actually like for example, for this chair, if you want to try to illustrate the fabric or like the blue color, then that's where textures come into play. And textures is where we actually sort of store that color data and that detail and apply it to those objects. But then you may be asking how, like, textures are just images, they're pictures, and they're like pictures on your phone per se, and that they're rectangular. They they they're clearly like a 2D thing. So how do we get them to apply to something that's 3D? Then the last component of that is what's called the UV system or UV coordinates. And do any of you remember in like geometry class, maybe in your high school or middle school or whatever, that we used to work with something called nets, where like it's like a cube flattened out or something like that? That's basically what UV is. You're kind of, and I'll try to find an example. Whoopsies. Uh, Cube net geometry. Yeah, something like this. Or the UV system will basically say through UV coordinates, you'll take a flat image like this that has your texture or your image data, what like the detail you want to apply to your 3D object, and you'll say that, hey, this part of it is going to go on this front face, this part is going to go on the top face, et cetera, et cetera, et cetera. It is a way of mapping a 2D shape into some three-dimensional object. So it is a little bit beyond like there's a whole art to UVing and how to most efficiently use that space beyond the scope of today's workshop, but um, so kind of good to know about. So if we want to start making up a 3D shape, the golden standard for all computer graphics is a triangle, because the least amount of points you need to make up a triangle is three, or to make up any shape is 3 points, which is a triangle. And so all meshes, basically every one of them, are eventually in some way represented as triangles. So in computer graphics, we have the classic teapot. This is used forever, like a lot when we're doing like or any sort of computer graphics examples, because of a variety of interesting properties, like it has the ability to cast shadows on itself. But it's more or less like the hello world of the computer graphics world, if you will. And it is composed of these triangles, and that's how you eventually get it to like build up to be a 3D shape. And each of these triangles, when you specify them, there's also what's called a winding to them. So when you go to specify, like, I want to make a triangle between these points, or when I'm placing the triangle somewhere in the model, it matters which way you specify the vertices. So in this example here, we have like a simple like 2D shape, but we have the vertices or the points like 0, 1, 2, 3. And when we go to like fill those in, we have to specify the order in clockwise order, because that's what Unity uses. And it's important that we do this because in Unity, only clockwise faces will be rendered. So, like, if you define a triangle like this and you were to flip it over, it would be completely invisible, because what you'd be looking at that point is like a counterclockwise ordering of them. I know it's a bit of a gibberish thing to kind of hear out loud, but like essentially, because Unity and many other graphics engines will only render one side of a triangle, we communicate which side of the triangle we want rendered by specifying the face we do want to show in the clockwise order. This is like kind of nitty gritty stuff, so not you won't necessarily need this for the shader stuff we're doing, but it's kind of important to know about at some level. And I suggest, if you're ever interested in learning more about this stuff, you can take a computer graphics course here. I think it's 427 or something like that. You'll learn more about this in depth. And also, we don't have to spend too much time with this, but like kind of going what we said about the UVs earlier, it's like this like kind of 2D map that we're applying to something in 3D, but kind of folding it up. And the way we do this as well is we give each vertex like a UV coordinate on some texture, and then that's what's going to be used to map stuff up. And these UV coordinates are normalized between 0, 0, and 1, 1. So every UV coordinate ranges from somewhere on like the unit square. And that's done to kind of be a bit more generic, or like not generic, but it's done to be easier to work with in the long run. Like you don't have to worry about how many pixels are in your texture. That can be variable, because ultimately you know that like 0, 0 is like the bottom left and 1, 1 is the top right corner. But yeah. So enough of that. That's all like the technical stuff. But we can actually go now and kind of operate at a higher level, where we just want to build uh, cool, fancy effects. So the way we do this in Unity in a really visual and intuitive way is something called the shader graph. And it is similar to a lot of other 3D workflows in that instead of writing code, or instead of working with all these like meshes and triangles and stuff directly, we have this nice, pretty graph that lets us sort of gradually craft the 3D effects that we want to make. And I think Blender has something similar. Blender has like a geometry nodes and like its own kind of shader graph of sorts. Oh yeah, yeah. But like the really nice thing is that this kind of workflow of like working with shaders in this way is generalizable to a lot of 3D applications. So we're going to be focusing on Unity today, but the principles that hopefully you can learn from here will apply to stuff like Blender as well. So I actually have Unity open here, and I put the project earlier in the announcement. So if you want to follow, you can download that. But basically in Unity, if you want to make sure first that you have the shader graph installed, so you can go down to Window, package manager, and then that will kind of bring up this window with everything that you can install. And if you go to, let's see, Unity registry and scroll down, you'll eventually see Shader Graph down here. I already have it installed, but you want to be able to install that, or you want to make sure you install that before you continue. Once you do have it installed, now it's time to actually start working on your graph, but you have to create the graph first. And so we can do that by right clicking, like kind of empty space for the folder you want to put it in. You go to create, uh, and then you go to shader graph up here, and then URP, and then you can specify either a lit or unlit shader graph. For if you're following the template, then you'll probably see this URP drop-down menu. Otherwise, you might see like some other options here. You might just see blank shader graph. But we'll get to the differences between those later. But for now, I'm just going to start with a lit shader graph. I'm going to call it my graph. And I double click it. And then I am now brought to the shader graph interface. But sure. But you know what is this? Actually, this might be hard to see because you know you have dark mode. But let's see if we can get it a bit darker. There you go. What's going on here? We have these two ominous boxes that say vertex and fragment. So what are they? Well, uh, these are sort of the ways we can start specifying uh, the outputs of our shader, or like where we want to eventually end up. These two, the vertex and the fragment boxes here, this is where you're going to output to. So on the left, you're going to do all of your calculations. And eventually, when you're done with everything, you're going to send it out to these things, which will ultimately be like sent out to the screen. So it's like this kind of is like your end goal here. You're trying to specify this data, whether it be your position, um, like the color you want to render, how metallic you are at a certain point, yada, yada, yada. So that's sort of the output. And for convenience, you even get like a little material preview on the bottom right, which is displaying what your work looks like so far. So right now, this is just basically a gray color uniformly across the surface. And so you get like a gray preview here. And last but not least, on the left, you can define shader parameters. So let's say you make a really cool shader, but you want to be able to specify, you want to be able to tweak some parameters. Like maybe I want it to be, I want to change the accent color from like red to blue. Well, what's nice is that you can specify as a parameter. So you can say there's a option, you can vary the color for this option. And this will ultimately be what appears in the material. So when you, any parameters you define on the left-hand side, they'll show up as like adjustable properties in the material that you can kind of customize to your liking. Uh, and I can show an example of this, but I know like I've gone over a lot really quickly. Are there any glaring questions or confusions or anything like that? Yes. So we'll look at an example later, but the vertex shader is basically uh, is going to represent how we change the physical mesh of whatever we're trying to draw. So let's say we're drawing a cube. What we can do is that we can actually, by changing the position output, we can actually move that cube or like shear it or something like that. We can apply some sort of physical distortion to it based on like our calculations. And we'll do like a live demo of that working. So that'll be a bit more obvious. Alrighty. Yeah. Messing with the normals. Um, so you may apply some like physical deformations to what you're trying to draw through the vertex shader. But it's not necessarily enough to just change the position. Like normals are supposed to represent like the, you know, the vector normal to the surface. So basically like the which way it's facing. And if you like, so for example, if you like, what can I crush? Because okay, imagine I had like a oh okay, I'm sorry, your issues. Like if I crush this, right? Like I have changed the positions of like these like like the vertices upon this pore tissue box. But now the each individual vertex on the surface is now pointing in a different direction as a new normal. So as yes, we've changed the positions, but now we must also change the normals to reflect what we just did. So that's where you might need to manipulate normals. I'm sorry for that tissue box. Okay, great question. Normals are basically like it is the direction that like a surface is facing. So if I have some sort of like cube like this, the normal of this surface here would be kind of like a vector pointing out like this. It is basically like the technical term, it's the vector orthogonal to the plane or like it's perpendicular. So like you can even take this into like a two-dimensional case where if you have a line like this, the normal of that line is like the perpendicular vector. So it's like perpendicularness. It's I know that's kind of mathy. Yeah, it's like the direction that any particular point like is kind of sticking out at. So for like this chair, like if I kind of like this mark would represent the normal, and you can see as I kind of go across the surface, that direction changes like that. So you this marker represents the normal at any point in the surface. Does that make sense? Yeah, precisely. And so like you can see that like as I go across the back surface here, that normal, yeah, it'll go like out like that. So you can kind of imagine that normals are defined across the whole surface, and that's what you. And the reason why we have them, because yes, it is confusing. But the reason we have them is for lighting calculations. Because if you want to calculate like how much light you need to reflect off the surface, you need to know basically which way you're like how you're going to reflect light off of it. A lot of computer graphic stuff, I promise, like it's not. You won't need to know that much ultimately to do these effects. But if you want to learn more, a computer graphic course or something like that. Any other questions? Because I know it's confusing. It's a lot. Okay. I'm also hungry, so I might be rambling. But we have pizza coming, like I said. So stay tuned for that. 5:30. 5:30 downstairs. Okay. So when we want to actually start doing any sort of calculations, we introduce shader nodes to the graph. And this is basically any way to either specify data or manipulate it in some way. So we have this really simple example. So each of these like big rectangles, this is a node. So we have one color node here, one color node here, and an add node. And once you've specified these nodes, the way you actually connect them together to do something is through edges. So because we're adding red and green together, or that's what we're trying to do. This is trying to add red and green together. We draw an edge from like the red color to the one parameter of this add node, and green to another parameter of this add node. And that is how we ultimately connect them together to output yellow, because red and green, when you're doing added a color, that makes yellow. And basically every like there's tons and tons of operate nodes for like different sort of math operations, or like if you need a sample of text, if you need to go like get a particular pixel on the texture, you're going to do that through these nodes, and you're just going to connect this data together, and eventually you're going to get like a fully connected like you're going to draw edges all the way through, and then eventually your edges will connect as we like saw in the previous slides. They'll eventually you'll have edges connecting to these things because that'll output data. Um, so I can show you an example of this. So very basic. I'm going to go get a color node. So this allows me to specify any color, right? And I'll kind of expand this so that it's a bit more obvious. I'm going to set the color to red, and I'm going to connect, like I'm going to output it by creating an edge by dragging from this output point here into this point here. And then now it's red. So this is a very basic, like kind of example. But as you can see, we have like some sort, we have a piece of input here, and then we're just connecting it through an edge, and that's how it's like flowing through. Any questions? Okay. Uh, so I mean, we can keep going. Like you can add any, like there's tons of like different types of nodes. As I said, there's like multiply, there's like a sine wave, all this fun stuff, and ultimately you can create some. I don't know. You can create whack things by just kind of connecting all this together. I don't even know what this will do, but like this is how we string together operations in order to like output something. So like I can actually take a value of, I can introduce like a float, which is basically a decimal point number, and I can feed into this multiply operation. And then like if I pass in zero point 0.5, that's going to make a slightly darker version of the red because I'm like halving the amount of red that's available. This is a very wacky example, but it serves to show that like to reiterate it, you're stringing together all these operations. You're kind of going from left to right in order to eventually calculate at the very end. So I'll delete that all for now. But it may be beneficial to focus exactly on the differences between like, so we have a vertex, a thing here that says vertex and a thing here that says fragment. So what are we actually trying to output? Well, uh, a vertex shade. So the vertex box represents a vertex shader, and is basically a calculation you do for each point or vertex on the mesh. So if you have a cube, each vertex is a corner on the cube, so there's 8 total. The vertex shader would be run 8 times, one for each cube. And this is how work is divided on the GPU within vertex shaders. You're dividing up the work amongst the vertex. So you only get that vertex's input, and that's it. So you do some calculation for that one vertex within the shader graph. On the other hand, fragment shaders, or like this fragment box, these are run for every time, for every pixel that is occupied on the screen. So in this sort of example here, um, we have this like sphere, and we have a bunch of pixels that like on the sphere here. And even if you come up closer to here on the board, you can kind of see the grid. But basically, our fragment shader is going to run for each like pixel that's drawn here. So like there's a row here, all the way through. So like every time you pass something to the fragment shader, you do something in the fragment shader, you're working on one particular pixel on the screen. So basically, the workflow is that you physically do any transformations to your mesh first. So you modify the physical shape first, and once you decided on that, you then work to coloring it in. So you can, if you want to imagine an analogy, like you have a, like those like coloring books or whatever. Like here, you're defining the shape of that coloring book, and then here you're filling like the fragment shape. You're filling in those colors. That makes sense a little bit. Uh, so yeah, to help reinforce this, let's actually start like doing some meaningful operations that'll like help us understand the difference between the vertex and the fragment shader. So we're going to start with vertex. Our goal is we're going to make a really simple shader that is just going to make whatever we pass into it bigger. And we're going to do that by multiplying each vertex by some scalar amount. So in this example on the screen, we are multiplying each vertex by 1/2. That is to say, for the x, y, and z coordinate, we're all multiplying them or by 1/2. And this is going to, in effect, shrink the model. So let's see this in action. First off, if I'm going to multiply, if I'm going to take a vertex and shrink it or multiply it in half, I actually need to get the vertex I'm working on. We know that the vertex shader is going to be working on each vertex in the model, but I actually need to get that vertex so I can do something with it. And the way you introduce that input vertex into your shader graph is by using the position node. It's under input geometry position. And this is basically saying, where is this vertex in 3D space? Um, there's many different ways you can get this information. You can hit this drop down and you can basically ask, where is this vertex in object position and view position, world position, tangent? These are very complicated terms you know, I don't want to confuse it further, but for the sake of simplicity, we're going to go for object space. This is basically, where is this position relative to the model itself? So this is not going to change. Even if you move like the sphere or object around the world, it's always going to be defined, like it'll be the same relative to itself, which will be important. Um, so we have our input position, and now we are going to half it. So I'm going to do a multiply, and I'm going to add a float, or basically a decimal number. And I'm going to add the position to one operand of this multiply thing. I'm going to add the float to the other, and I'm going to specify, instead of 0, 0.5. And then I'm going to connect this to the position node, and voila, it is smaller. We can even, we can tweak this. We can make it 2 to make it really big, or maybe 0.75. But as you see here, we are able to physically modify the shape of it very quickly by using like a vertex shading setup. Any questions? Because I know I'm kind of rambling a bit, and I do apologize for that. But I hope, at least intuitively, this kind of makes sense that we're just applying like this simple multiplication per each vertex, which ends up like shrinking it in the end. Say again? Oh, fantastic question. So a lot of the times, um, when you get these previews, what it's going to try to do is it's going to try to visualize the input data. So, and it will try to visualize that in like using RGB. So we specified like uh, we're specifying positions which are measured in X, Y, and Z. And so what it's going to try to do here is like visualize the X, Y, and Z stuff using like RGB or like through color. So the X would correspond to the red channel, the Y would correspond to the green channel, and the blue would correspond to the Z channel. And we can actually kind of see this here. If you imagine like this being like a 2D graph, um, you know, when you have negative X, negative Y, you don't have any color. You have negative color, which is basically, or more or less, that's black. Does that make sense, right? Black here. If we have positive X values, but negative Y values, we're just adding red. So we see here where it's just red down here. Likewise, in the this quadrant up here, we have positive Y values, but negative X values. So this is green. And this quadrant here, where we have positive X and positive Y and positive X, we are adding both red and green. And because, computer color is additive, red and green, when you add them, makes yellow. That's why, like, kind of down the diagonal, we start seeing yellow. But that's a great question. Say again? Okay. Uh, another fantastic question. So consider our friend the tissue box. If I define the center of this tissue box to be like its like literal center, like right in the middle of this, object space would be where each of these like positions or vertices are relative to its center. So it doesn't matter how I do this, right? If I flip it, if I move it, sorry, um, it's not going to change because it's relative to the object. If we specify in world, now the data you're being fed into is like, where are these vertices relative to like the room you're in or the environment? So as I move with this poor tissue box to the side, I'm like, assuming that this is the right direction, this is the left direction, all these vertices are now going in like a negative x direction. So like we are like the further I move this way, the less these x values become because I'm physically moving them around the world, hence world space. Most of the times when you do shaders, you want to work with object space because you want to apply an effect sort of like you don't want to necessarily care about where it is in the world. You just kind of want to apply it to the object itself, and that's where we use object space. That's also a good question. Any other questions? Yes. Most likely, or just like there's various techniques to make it look very weird, but yes, one of them is like you can do things in a world space thing. Um, let's see. One example I can show later for extra stuff is sometimes you do want to have world space. I wanted to make a shader for my like the weather. You can come inside. You can have a seat. Or oh, okay. We'll carry on. Um, I wanted to make like a. I well, anyways, I wanted to make like a grid effect where uh I make the floor or like into like a grid that like corresponds to like each square is like 1 meter intervals that are aligned with the world coordinates. Then I want world coordinates because then I want to like draw like the squares depending on where they are in the world. So that way I can move the object and it has like this kind of weird effect where like the grid will stay stationary but like on the object. But yeah. You kind of get the point. Um, let's see. All right, but we hard coded per se that half value. So we specified it directly in our shader that we wanted the half value, but that's not very flexible. If I want to make like, maybe I want to have like a big shader and a small shader, I don't want to have to make two separate shader graphs. This stuff is already confusing as is. I want to be able to kind of have some flexibility by introducing a parameter. And that, oh, I see. Thank you. Okay, will do. And so if we want to have this flexibility, we can start introducing a parameter. So if I go back here, I'm going to first create, to demonstrate my point, I'm going to create a new material that's going to use the shader I just made. So when I create the new material, and I'll call it like my cool material, I'm going to have it use the shader that we just made. And I called it my graph. But you'll notice now there's nothing. And that's because there's no parameters here whatsoever. We haven't added any yet. But we can still apply it to like a sphere. If I add the sphere and I add my cool shader thing, now when I drag it on, it gets smaller. So like everything still works as before. If I come here and change the value, now the sphere is much bigger. So like our shader is working, but we can't, there's nothing here to adjust. And we want to add that flexibility by adding like an option. And what we do instead is we come down here to this little menu on the left. We'll hit the plus here. We'll add a float parameter or a decimal parameter. And we're going to call it size. And now that I've defined that, I can actually drag it into the graph. And you'll notice here that there's a circle. It's like an input that we can start actually feeding into things. So now I can connect it over here like this here. So now instead of this like, manually specified value, we're having a variable here that we can modify to our liking. And if you click on this variable here, you can also see that in this graph inspector up here, like in the settings, you may need to click this button up here, this graph inspector. We can change its default parameters. So right now the default of this is going to be 0. I'm going to set that to 1 instead. And I can hit save. And now, when I go back here, now you can see that we have a parameter here that we can adjust. Is that 1? Oh, okay, great question. Um, like, how do I apply it to the sphere? One way in Unity is that you can just drag it onto the thing that you want to apply it to. Oh yeah, yeah. Yeah, so you can drag it on. You can also, when you click on something, ultimately your material is stored in what the mesh renderer component. So you can also drag it into this thing, or you can hit like the circle here and find it many different ways. But the simplest and most intuitive is just drag it on. Alrighty. But now you, or what? Oh, let me see. Oh, okay, yeah. The reason there, I should probably make it more clear, is that those are shader graphs. So you have to actually create a material using those shader graphs. Yeah, so apply what now? Ah, yeah, yeah, here. I'll do it up here. Oh, 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 my bad. Here up here for any material, you can specify what shader uses by this drop down box here. So you click on it, and then you can search up. Uh, hopefully, your shader graph will appear in the options, and then you just select it. Does that work? Yeah. And then when you're going to apply the material to something, uh, you just drag it in. Okay. Now we're going to try to do something a bit more interesting, because the thing here is that we scaled the sphere to be bigger or smaller, but we can already do that within Unity. We can just affect the the scale parameter to make it bigger and smaller. Why go through all this extra complexity? Well, it's because we haven't really tapped into it yet. And this is where we're going to start doing some funky things, which don't feel stressed out or alarmed if you don't understand it, because it's going to be a lot of math wizardry to get things going. It's it it's something you kind of have to get used to over time through practice. But ultimately, I'll try to, feel free to ask questions. I'll try to break it down as much as I can. But basically, we're going to start adding these additional effects that we're really going to show the power of these shaders. So what we're going to do right now is we're going to try to introduce time. We're going to have like our sphere kind of wobble back and forth. And we're going to do that by basically taking the position, and we're going to sort of add to it, and we're going to multiply it to try to create some sort of oscillation. So I'm going to go back to the shader graph, not that one. So here now, what I'm going to do is I'm going to add a time node. And what the time node does is that it lets you take as input all sorts of time values. By default, the one you're going to use the most up here is called time. And this is basically a variable that stores how many seconds have passed since your shader has been created. So as you can imagine, the longer that you draw to the screen, that time value is going to go up. And what I'm going to just do, if I look here, let me go to slides. We have this also another different time value here called sine time. And basically, what all this is going to do is feed the current time value, or is how many seconds have passed, into a sine function, and then you're going to get the output of that. So that's going to be somewhere between -1 and 1, and it's going to oscillate over time. What I'm going to do is, I'm going to here, I will first add a multiply node, because right now this sine time is going to go between -1 and 1, but I want to sort of decrease its intensity. Oh yeah, you can also see that kind of effect going. It's going brighter because it's like oscillating. And I'm going to make it less intense by multiplying by 0.1. So it's going to be 10% is intense. I'm then going to go make an add node. And use this as reference. Yep. Let's kind of code this out real quick. Yeah. Okay. So, uh, oh, Ian, the pizza guy is on his way soon. Whatever. Yeah. No. 5:30. Okay. Okay. So, what did I just do here? You'll notice now that our sphere is kind of breathing. It's expanding and it's contracting. And the way we've achieved this is we're basically first getting our sine time. We're basically getting that sine wave that slowly oscillates between -1 and 1. So we start here. I don't want it to grow that big or that small. So I'm going to take whatever value here and multiply it by 1/10. So instead of -1 to 1, that's going to be negative zero point 0.1 to positive point. So a very small range. And then I'm going to add 1 to it because basically, if I were to feed this directly into the cube, that would be oscillating from 10% size to -10% size, where the sphere kind of warps in on itself. So I add 1, so now it's going to be fluctuating between negative or zero point 0.9 and 1.1, or aka 90% size and 110% size. And then I take that sort of percentage, I multiply that by the position now, and when I output it, now we get this breathing effect, where it kind of is expanding and contracting between 90% and 110% size. Does that make sense? Oh, like why is it where is it not oscillating like in these things? Um, yeah, here. That's a good question. Let's see if I can try to exaggerate it a bit. I'll make it like instead of zero point 0.1, I'll do 3. Okay, so because this data is being interpreted as colors, it's not going to physically change the shape of the thing here. It's just going to change the colors. But you can see that it is actually correctly visualizing it because we are like sort of we are intensifying like if we apply this into like a color space, we are intensifying and also darkening our colors. We're like we're oscillating like that. We're even having this funky thing where like the sphere is like inverted. Crazy stuff. But that's why I kind of wanted to like, you know, 45. So that's a good question. But that also brings up a good point is that like as you sort of build these effects, you can see sort of the intermediate stages in between to help you kind of understand what's going on and whatnot. Any questions? Because I know it's like it is kind of a funky topic. Yeah. Alrighty. Also refresh it. Okay. But still, in Unity, we can make a script that kind of manipulates the scale value and makes it grow and shrink over time. So we haven't really done anything too tremendously cool yet. Now I promise we're going to get into the cool stuff. So whoopsies. Now we're going to introduce some wobble. That is, instead of uniformly scaling it up and down, we're going to try to manipulate the scale at different points or at different vertices to kind of get this wobbly effect. This looks scary. It requires a bit more math. And frankly, I don't remember what that math is. But I have like the end product in this project, so I can kind of just show you what it looks like and break it down. So I think in the project, it's called, let's see, it might be, I think it's called example. No, not that. Here. Uh, it's called My Shader Graph. How descriptive. But I can basically try to run you down like through what it's going step by step. So to see this. So in order to modify it like this, basically what I tried to imagine first is that you have sort of like a sine wave or like a wave going through the object on a particular axis. So I just chose, I believe, the x-axis. So what I need to do functionally to get this effect is that I need to take the position and I need to individually consider its x, y, and z parts, and then like either scale or move the vertices as like a result of that operation, or like as a result of like where it is on the x sides or whatnot. So I'll kind of try to explain it front to back. Um, yeah. So first, I take the position, and then I feed it into a split node. And this is basically trying. What it does is that it takes any position or any like kind of like vector, color, whatever you get, and it splits it up. It splits it up into its individual parts. So uh, for positions that are in 3D space, you have an X, Y, and Z. The split node will split this up into the X, Y, and Z, where you can get those values individually. If you were to provide a color into the split, it would also um, it would provide you the R, G, and B values of that. So for one of these X values, I take it as input to this add thing here. And what this does is that this takes in the current time, which I multiply by some time scale parameter. So as you notice, if I take this time scale parameter and I give it a higher default value, it's going to start oscillating faster. So I'm just scaling time to be bigger or smaller, right? I add this together with the X value, and then I then take that resultant value and I multiply it by some other parameter called what I call wobble wave length. And by multiplying the output of this, the first multiplication let me change the rate at which it was oscillating. Now, if I multiply the output, this lets me control like the actual how long like the wobble is per se. So if I multiply it by some really high value, now I get really sharp wobbles, and um, I can make this really crazily high for like a lot of wobble. Uh, and the reason why this works is again, it's a bit of a math thing, but basically, um, this add and multiply here is supposed to be like an offset that I'm like adding to each of these positions. So by multiplying like this like delta or this offset thing, I can increase like how much it's gonna be shooting up into the sky or whatnot. So that's what gets like these big wobbles or whatnot. Then I feed this value into a sine function so that it kind of oscillates between -1 and 1. Uh, and I have another opportunity to apply another multiplication that will allow me to change how, I think this actually, yeah, this changed how like the amplitude of it or how far up and down it's going to wobble. So whereas our previous scale called wobble wave length kind of controlled the length of the wave going through it, this will kind of control the amplitude. I wish I could draw this on the board so it was a bit like kind of simpler. Uh, oh, corner markers. So this kind of parameter here, this would be the wobble length, like this distance here. That's the, I believe, what I called it, wobble scale. And what else? Um, the time scale is basically like this distance here, like how what like uh or it adjusts the frequency. So I guess it's not technically length, but like it's like frequency. And I know I'm not doing like the best of jobs kind of explaining all this math, but that is a lot of what shader programming comes down to is like being able to recognize patterns within these using like a bunch of math to create effects like this. And I can provide you with the slides afterwards. I can provide you with a bunch of resources online. But when you string them all together, you can get like these cool kind of effects. So now if I save this and I go to the materials, I have a material here ready to go that's already using these parameters. So if I drag it in, now we get this cool wobbling effect. And I can, I can make that wobble less intense or like kind of decrease the wave of it, introduce less wobbles. I can make it wobble really fast, you know, way too fast. And then I can also make it wobble further up and down. Yeah. Yes, correct. So right now it's wobbling just based on the X parameter, but let's see what happens if we kind of change that. What should we do instead? Sure, we can change it to Z. So right now, we the way this works is that it manipulates either X, Y, or Z, and then this process back here kind of adds it all back together and reconstructs it to, and then outputs it. So what I'll do instead is I will instead feed Z into this, and if I hit save, now like beforehand it was kind of wobbling like this, like front to back thing. Now it's kind of doing it side to side. So like kind of changing like the parameter we give here as input, like it affects like how we do the calculation. So if I feed y into here, now we kind of get these really interesting vertical wobbling. But that's kind of the magic of shader programming, because a lot of this stuff, you don't like, you can get a lot of cool stuff just by kind of messing around and seeing what you can kind of create, um, and whatnot. Yes, 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 perfect. So I can spend a bit more time on that. Okay, so to do an effect, like I'll kind of reset it. So I'll also put this in play mode so that it kind of keep wobbling even faster. Click away. So to do an effect like this, right? Um, I need to vary the wobble or like the scaling or all the operations depending on where the vertex is in like the mesh. So like that is to say that like the vertices at the front of the sphere are going to move differently than the vertices in the middle of the sphere. So I need to like, and to wobble it in a particular direction, I need to care about like how far along like the x-axis that particular vertex is. So to do that, you know, this split lets me take in the position and boil it down to its individual components. So in Unity, the X represents your like left and right movement, Y is up and down, and Z is forward and back. So this is basically me saying I'm going to split you up to just let those individual like left, right, up, down, forward, back, and we're going to then take as input the left, right part of it. Um, Precisely. It is kind of confusing that way. Uh, yeah. Yeah. So oh yeah, well, I mean, eventually at some point, like the time values can overflow. If you happen to get any of your like, ah, yeah, of course. I do actually have the formula in the slides. Yeah, yeah, I can switch back to the slides. Yeah. Oh, so the Y there represents the original Y position of the. Oh, without that Y, if you don't have that Y there, yeah, because if you think about it, then you're just like then what you're left with is just the offset. So then you're basically losing all like your Y information because you're just going to go off of the offset. So everything kind of gets flattened. So basically, if it kind of helps you conceptualize, what you're really doing is Y plus equals this offset. You're taking the Y that it's at, and then you're offsetting it by some amount depending on this equation. I know, like I said, like, I'll beat a dead horse. It is kind of confusing this way, but uh, we can link to like YouTube videos about how to kind of do all these effects in detail. Um, and yeah, any questions? Yes, yes, um, yes. Is it? Yeah. So if I switch to a cube, it might make a bit more sense. So we are just manipulating the y position of each vertex, but we're doing it across all vertices. So so like if you were to laser focus on any particular well, this is wobbling way too much. um yeah, I'll make it like less okay, here you go. We can kind of laser focus on this. If you look at any particular vertex, right? If we're just following this, all this is doing is just moving straight up and down, right? And that's what we're doing. We're just manipulating the y value. But when you kind of add it all together, it kind of gives you the motion that like there's like a wave going through it or whatnot. Because we are offsetting, or basically we are changing like the offset depending on like how far along this axis is. And we can see another interesting effect. Remember how earlier we were talking about the difference between object and world space? Let's instead change the shader to use the object space instead of, or sorry, world space instead of object space. And now you'll notice is that as I move this, you can kind of see that sine wave come back. Because now we're taking like the world space as like the coordinate, and you can see that um, like we are literally just manipulating this x value. Because if I like kind of move it side to side, it doesn't really change up and down. Yeah. Oh, that's another good point. So whenever you do these visual effects, it's purely modifying the visuals. So if you want to like if you were changing the shape of something like your character or whatever, and you had colliders, they will not be affected by whatever you do in the shader because they're a completely separate concern. Like um like it purely shaders purely affect like the visuals that you see. So yeah, those are basically vertex shaders. Clearly tons of depth we can go into about like the different kind of cool effects you can do with them, but for the sake of time, And I know we're hungry too. I'll just kind of quickly go into like the fragment shader. So conversely, we just did a bunch with the vertex shader. The fragment shader is how we can affect kind of color values. And as a reminder, instead of operating per vertex or per position, we operate per like pixel that ends up on the screen. So we can, as part of that, we can take into consideration like where that pixel is, like where is its position in the world, and all that. But we use fragment shaders when we want to kind of change the physical, like the lighting of it, or like the colors or anything about that. And so what I like to do as kind of an example is like the M portal shader for Minecraft. Basically, it's this weird effect where if you look into it, it's like this sort of void within. Like there's like clearly kind of like a weird like there's a bigger space within. It's kind of hard to explain um, just through words, but I can show you what this means. But basically, I'll for the sake of time, I'll kind of go through the end product. Oy. Oops. It's this effect here. Well, you'll notice that like the stars kind of stay put on the even though we're kind of orbiting around it. Do you see that kind of effect? It's a bit weird. So what this is called a cutout shader because instead of this like being on the surface of like the object or like this cube, as the name implies, you're cutting out um yeah, hold on. Come on. Hello? Here. So we can take a look at this. For now, I was also wobbling like this top half is for the wobble, but because that's not really our focus, we want to focus on the fragment stuff. I'll just kind of push it off to the side. Mhm. Yeah, so for the M portal effect, we don't actually need to touch the vertex shader at all. We just oh oh that was probably from some previous example that like I was showing off, but then like kind of disconnected at the very end. So the way you get these like this sort of cutout effect or this end portal is that instead of taking the vertex position as input, you're instead wondering where is it on the screen. So instead of working with a 3D coordinate, you're actually working with a 2D coordinate because you're just considering this like screen rectangle and you're wondering where am I on the screen, and then you're coloring the cube based on where like the pixels and like currently is on the screen. So you can kind of notice if I like get right up close to the cube, you know, I am like I am actually strafing from side to side, right? But if I stay fully within view of the cube, you can't notice. It's because the screen positions of all these different fragments is not changing because we are only concerned about where this is on the screen. And so you can imagine that this is sort of like a cutout to like some picture image behind it. Ah, great question. So we'll explore that in the shader. Right, the other one, the M portal shader. Okay. So this one is actually, relatively speaking, pretty straightforward. So what we do is that there's another node called screen position. And what this does is that instead of giving you the 3D space coordinates of where of a vertex on your like object, you instead get the 2D coordinates of where it is on the screen. And that's what we need. Um, then what I do is to try to kind of get it to move a little bit, like to kind of flow across the screen. I then take the time, I multiply it by some scale value so that we can, or what? Okay, good. I scale it by some value so that we can affect like, how fast it scrolls upon the screen. And all I do is I add that value to the screen position. So basically, if, our screen position is like 2, 2, I then start adding the current time so that like, like a time of 5, so then it becomes like 7, 7. But because that time value grows over time, those values are going to shift along with it. So that's how we kind of get our like scrolling effect because we're adding time to the positions that makes it scroll. I don't know. I don't know if it actually has an actual name. Sure, you can. There's probably a formal name that I don't know. But then there's what's called a sample 2D texture node. And so basically you give it like a picture or a texture as input, and then it has a parameter called UV. And this is basically your way of saying, hey, I want you to sample the texture at this particular point. Yeah, it is a 2D vector. Oh, yeah. Uniform vector, maybe, because it is normalized. I don't know. I, I'll Google that afterwards. But basically, um, because this coordinate here is constantly shifting, by extension, where we sample on the texture will also constantly shift too. So that's how we kind of get this scrolling effect because we're basically kind of sampling like at like we're changing where we sample and that like adds this sort of like scrolling effect. And it's worth pointing out that UV coordinates also wrap around. So even though like these values are growing to be like, you know, huge or we're adding like time forever, so like it might go like hundreds or thousands, it's all going to basically wrap around the end. So it's going to try to constrain it to be between 0 and 1. So like in a mathematical sense, it's applying a modulus of 1. And so that's how we can kind of get this infinite effect without worrying about it. But any questions? Because this is basically like a really, it's a fragment shader, but like uh, we are taking the screen position as input, we're like offsetting it, and then we're sampling a texture, and then we're outputting it. And that's kind of this whole shader and how it works. Any questions? A sampler, like here, that allows you to specify the behavior of what happens when you sort of sample outside the texture. So you can actually specify that as a node. So we do sample state, and it has two parameters: filter and wrap. Filter specifies, let's say you have a texture that's like 4 pixels, or like a square of 4 pixels, like top left, top right, bottom left, bottom right. Filter specifies how you interpolate between those values. So let's say if I sort of sample in between like the top left and the top right square, there's no explicit pixel there per se. It's right in the middle. But do we just, you know, do we blend the two neighbor pixels together? Or do we just sort of like pick, like, we just pick one of them? That's what that's specifying. Uh, and you point would be like just round down, just take the nearest point color, and then linear is like try to blend it, and trilinear is like a fancier way to blend it. And then lastly, wrap, uh, it specifies how you sample the texture when you go outside the bounds. So this is actually a really cool way to demonstrate how our shader works, because right now we are relying on the fact that we repeat, or like when we go out of bounds, we repeat the texture, or because we do a modulus. But if I say clamp, it breaks, because now clamp basically says only allow values between 0 and 1. But because we're trying to sample at values that are greater than 0 and 1, we're like trying to sample at 700 or 700, 700, but relying on the fact that the sampler will just kind of wrap around, it breaks altogether. But if we set it back to, or say again? Yeah, yeah, yeah. When we do clamp, this like sampler node is basically going to assume for any points that you sample outside of 0, 0, and 1, 1, outside of that like unit square, you're just basically going to take the closest color on the edge and repeat it. So Like, to draw another example, I have this square here. This is 0, 0, 1, 1. In clamp mode, if I try to sample something like down here, what is this going to do? Is this going to go to the nearest edge and take this color instead? But as you can imagine, that kind of breaks our shader because, you know, we're only getting detail on the edge. Yeah, yeah, yes, yes, that is absolutely correct. So if we instead do this modulus ourselves, so we create a modulus node, we feed our coordinate into here, and then we sample. Oh, here, here. Yeah, we have the same effect. Because then instead of the sampler texture 2D node doing the modulus for us, we do it manually. And then so even though we're clamping, the effect is the same. Good question. Modulo is basically taking the remainder. So if you have like, yeah, mod. So like if you like 7 divide 5, the modulo is 2, or the remainder is 2. So in the same way, we do like this crazy high like coordinates, we're taking the remainder of 1, which is basically gets us back into that like 0, 0, 1, 1 range. Great question. Um, but yeah, other than that, that's basically uh the workshop. There is some further material here, for the sake of time and like to not cause confusion more. I'll kind of go over it very briefly. But basically, the other addition of shaders is that you can have lit and unlit shaders. Lit shaders will try to like take lighting into consideration and uh, like make things like add like shiny spots when there's like nearby light and whatnot. It doesn't look so good for our M portal shader because we have these like shiny spots. So what we had to instead do was switch to an unlit shader, uh, which basically it doesn't get affected by lighting at all, and whatever color you output in the shader gets sent directly to the screen. There's no extra lighting steps in between. And in Unity, you can kind of change whether or not it's a light lit shader by going up here into the graph inspector under graph settings, and up here there's like a drop down for material. Right now it's unlit. If we set it back to lit, we notice that like we kind of have these shiny spots because it's now trying to respond to light, but we don't want to do that because that kind of ruins the effect of our thing. So we switch back to unlit, and that gives us our like direct like whatever we sent out to the fragment shader, that's what's going to end up on screen, nothing in between. So other than that, that is basically the whole workshop. I understand it's like a lot of material, and it may have been confusing. That's part mostly on my end because I probably could have prepared a bit better. But ultimately, what I do want to demonstrate, what you do want to walk away from today, or is that you can achieve a lot of these effects through the shader graph just by applying like a lot of this sort of like math and like like these functions, and slowly like kind of building up an effect that you either send out and out of your fragment shader and a vertex shader, and that's how you can kind of cause these cool physical deformation effects, or uh, coloring and whatnot. There's tons of resources online if you want to like for people who can explain this probably in like a more concise manner than I can do. Uh, oh, rotate. But we'll provide that to you. We'll also like the workshop is, or the project files are in the announcements, and I'll also put like a few YouTube videos you want to follow at home. But other than that, or, or what? Or say again? Yes, 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 again. Other than that, we can finally have pizza. Sorry for the people at home. You don't get pizza.